Hi, this is Professor Fernandez. This is video 3 in lesson 11. We're talking here about higher order derivatives, and I will tell you about that through two examples from Calculus Simplified. So higher order derivatives, what does that phrase refer to? So we know, for example, that if we have a function, let's take x squared, a simple function, we can take its derivative, right? And that's a power rule application, that's 2x. By the way, check out video 10.2 for a discussion of the power rule if you need a refresher. Okay, so we can calculate 2x. That's the derivative of x squared. What if I now just called 2x some other function, g of x? I didn't know that it was the derivative of x squared. Somebody just gave you the function 2x, and they asked you calculate g prime. Okay, well, this is a linear function with slope 2. Its derivative is 2. There you go. You can do that. But notice that g is just f prime. So what you've calculated here is the derivative of the derivative. We call that the second derivative of f. Okay, so now we have a little chain of differentiation here. If f of x is x squared, its derivative is 2x, and its second derivative is 2. You can see that I no longer want to call f prime the derivative. We'll still use that term, but now there's a new context because this is also the derivative of a different function, right? It's, in this case, the g of x, or the derivative of f prime. So now that we have multiple orders, right, higher order derivatives, multiple orders of derivatives, we call this the first derivative. We call this the second derivative. And as you can imagine, there is certainly even more. I could take the derivative of this function once more. We know that the derivative of a constant is 0, so I would get f triple prime, third derivative, equals 0. So you can keep going, right? The derivatives for this function, f of x, beyond order 3 are not very exciting, right? The derivative of 0 is 0. That's the fourth derivative. The derivative of 0 is 0. That's the fifth derivative, and so on. But for different functions, derivatives get more complicated, more exciting, more interesting, and they might tell you more about the function, something that you would learn specifically about in Calculus 2. Okay, so that's just a very quick intuitive introduction to what the term higher order derivatives means. It means differentiating more than once, effectively. So let me actually do this example down here first, because this one asks only for the second derivative, and I'll go back to this example and explain this notation afterward. Okay, calculate g double prime second derivative for this function. So at this point, I want to calculate the derivative, g prime, and then calculate the derivative of that, getting the second derivative. Okay, we need to determine which differentiation rule to use here. We might notice that g of x is the square root of x plus 1. So that's kind of a tip-off that this is a composite function. And I'm going to write it here as x plus 1 to the 1/2. So the rule that we're going to use here to differentiate this function is the chain rule. So if you want some refresher on the chain rule, you might want to check out video 11.1 where I talk about the chain rule. If I apply that here, what am I doing? I'm differentiating the outside function, which is something to the 1/2. The derivative is 1/2 something to the 1/2 minus 1, power rule. Evaluating it at the inside, and then multiplying it by the derivative of the inside. Okay. And then from here on, it's just simplification, except for that little term. We'll get back there. So 1/2 x plus 1 to the minus 1/2 times the derivative of x plus 1, linear function, slope 1, the derivative is 1. So then I can stop here, but I'll rewrite it in slightly simpler form by putting that downstairs. 1 over 2 square root of x plus 1. So that is g prime of x. Okay, great. But I'm not done because we want a g double prime of x. So I want to go down here and calculate the derivative of this. The best way to do that is actually to go back one step and write it in this form, because that is the chain rule form that is most useful for us for calculating the derivative of this new function. Okay, so the outside function here is 1/2 something to the negative 1/2. The inside function is still x plus 1. So the derivative of this, which is now the second derivative, brings down the minus 1/2, subtracts 1 from that, and then evaluate it at the inside times derivative of the inside. Okay. So you can see how what I've done here, I'm putting brackets here because I want to keep the 1/2 outside. This is effectively the constant multiple rule, which we talked about in video 10.1. So now let me just do some simplification. So I get minus 1/2 times 1/2, that gives me minus 1/4. X plus 1 to the minus 1/2 minus 1, that's minus 3/2. And then derivative of x plus 1, same as it was over here, that's just 1. So this is the answer, but let's simplify it just a little bit. So I get minus 1/4 x plus 1 to the 3/2. Or we could put a radical in there if you want to do that, and this would be the square root of x plus 1 cubed. We can pull out, a factor of x plus 1 squared, take the square root, do all that stuff, but at this point, the video would become more about the algebra than the calculus, so I'll stop here, and then zoom out for this problem and say that, again, the initial idea is to, at this point in the course, recognize the function you're dealing with. Is it a power function? Is it a quotient? Is it a composite? Because then you can determine which rule to apply. Even if you have to do it more than once, right? At least you'll have a guiding strategy for how to differentiate this function. Okay, so now let me go back to example 3.42 up here, and let's see what this says. So calculate this thing for x cubed. Okay, fine. So you might be wondering, what is this notation? Haven't seen it before. So this notation is the nth derivative of f of x. We're thinking of n here as a natural number. In other words, 1, 2, 3, 4, going on forever. So long story short, this means calculate all orders of derivatives. Okay. So when you see a problem asking for fn of x, it's asking for you to calculate all of the orders of derivatives of the function. That may seem like a lot of work, and indeed for most functions it really is. But for some functions it stops being a lot of work, and we kind of talked about that. That's why I led with the f of x equals x squared at the beginning of the video. So let's see what happens for f of x equals x cubed. So let's start our calculation. This involves the power rule, which we talked about earlier, I believe in video 10.2 if you need a review. The derivative of x cubed is bring down to 3, subtract 1 from the exponent. Here we go. If I differentiate that again, I would bring down the 2, multiply with the 3, get a 6, subtract 1 from the exponent, x to the first. Now I find the derivative again, third derivative. This is 6x, linear function. Derivative is the slope, 6. And now, we could do f, 4 primes, but you can see it starts looking a little weird. So at this point, most of us default to or switch over to the parentheses notation. So this now means the fourth derivative of f of x, of f. And that's the derivative of the third derivative. Third derivative was a number, derivative of number is 0, so fourth derivative is 0. And at this point that we've differentiated to 0, any other order derivative, right? Higher order derivative, the 5th, the 6th, the 7th, it's going to be 0 because the derivative of 0 is 0. So we're going to say fn of x equals 0 for all n greater than or equal to 5. And that is, well, I would put all of this in as the answer if I were giving this on an exam or something, because you've done what the question asked, right? For the first 4 orders, you have different answers, right? The functions or numbers you get are different. But for the remaining orders, right, all the answers are the same. The function differentiates to 0. Okay, so I'll zoom out and mention one more quick thing. Higher order derivatives really is about differentiating more than once, right? And then notation, if you look at it for as many order derivatives as you want, that's what this fn means. And then last thing over here, sometimes, this didn't happen in this example, but sometimes, you'll differentiate once and you'll have to use a certain rule, let's say the product rule. And then when you differentiate again to find the second derivative, you will need a different rule, maybe the chain rule or the quotient rule. So this is one of the reasons this video is toward the end of this section on derivatives, because as you differentiate more and more orders, you end up potentially having to use a mixture of different rules at different levels or different orders of the derivative. Okay, thanks for watching.